Previously, we studied that the magnetic field produced by a current loop is proportional to the loop's magnetic dipole moment. In the same way, the additional magnetic field produced by a microscopic electron current loop is proportional to the total magnetic moment mu total per unit volume B in the material, and we call this vector quantity the magnetization of the material, denoted by M. The additional magnetic field due to the magnetization of the material turns out to be mu naught M, where mu naught is the same constant that appears in law of Biot-Savart's and Ampere's law. And when such a material is completely surrounds a current carrying conductor, the total magnetic field B in the material is B naught plus mu naught M. Here B naught is the field caused by the current in the conductor, and a material which shows such type of behavior is said to be paramagnetic. The result is that the magnetic field at any point in such a material is greater by a dimensionless factor Km, called the relative permeability of the material. Then it would be if the material is replaced by vacuum. The value of Km is different for different materials. For common paramagnetic solids and liquids at room temperature, it ranges from this value to this. And all the equations which we study in this chapter that relate magnetic field to their sources can be adapted to the situation in which the current carrying conductor is embedded in a paramagnetic material. So in that case, all that need to be done is to replace mu naught by Km mu naught. So this product is represented by mu. It is called the permeability of the material, and the amount by which this permeability differs from unity is called magnetic susceptibility, and it is denoted by chi m Km minus 1. This is magnetic. And this is permeability. So both Km and chi m are dimensionless quantities, and value of magnetic susceptibility for different materials are given in the book, in the table, which I am not showing here, so you can get an idea about these quantities. For example, for aluminium, the value is 2.2 to 10 raised to power minus 5, and Km for aluminium is 1.0000. And one more point is that the tendency of atomic magnetic moments to align themselves parallel to the magnetic field where the potential energy is minimum is opposed by random thermal motion, and which tends to randomize their orientation. So for this reason, the paramagnetic susceptibility always decreases with increasing temperature. So in many cases, it is inversely proportional to the absolute temperature, and the magnetization can be expressed as M is equal to C B over T, and this is Curie's law, and here C is a constant. It is different for different materials as Curie constant. So in most paramagnetic substances, a body which has atomic magnetic dipoles is attracted to the poles of the magnet. We already knew this from the previous knowledge. In previous lectures we discussed this one. So in most paramagnetic substances, this attraction is very weak due to this thermal randomization of the atomic magnetic moments. That's why a magnet cannot be used to pick up objects made of paramagnetic substances. But at very low temperature, the thermal effects are reduced, the magnetization increases according to the Curie law, and the attractive forces are greater. Now there is one more behavior of magnetic material. This is called as diamagnetic behavior or diamagnetism. In some materials, the total magnetic moment of all the atomic current loop is zero when no magnetic field is present. But even these materials have magnetic effects because an external field alters electron motions within the atoms, causing additional current loops and induced magnetic dipoles comparable to the induced electric dipoles. So in such cases, the additional field caused by these current loops is always opposite in direction to that of the external field, and this type of behavior is also explained by Faraday's law of induction, where an induced current always tend to cancel the field change that caused it. So such type of materials are diamagnetic. They always have negative susceptibility, and their relative permeability Km is slightly less than unity, typically in the order of 0.990 to 0.9999 for solids and liquids. And diamagnetic susceptibilities are very nearly temperature independent. Now the other important, the third and the most important one is ferromagnetic materials. This is the third class of material. We call them ferromagnetic material. For example, iron, nickel and many alloys containing such type of elements are ferromagnetic in nature. In these materials, there are strong interactions between atomic magnetic moments, and it causes them to line up parallel to each other in regions called magnetic domains, even when no external field is present. So here is in this figure, there an example of magnetic domain structure is given. Within each domain, nearly all of the atomic magnetic moments are parallel. When there is no external field applied, the domain magnetization are randomly oriented. Okay, but when a magnetic field caused by some external current or by some external source is present, the domains tend to orient themselves parallel to the field. So the domain boundaries also shift. The domains that are magnetized in the field direction grow, and those that are magnetized in other directions shrink here. Because the total magnetic moment of a domain may be many thousands of Bohr magnetons, the torques that tend to align the domain with an external field are much greater than occur with paramagnetic materials. The relative permeability is much larger than unity. It is of the order of 1000 to 100,000. So as a result, an object made of a magnetic material such as iron is strongly magnetized by the field from a permanent magnet and is attracted to the magnet. And for many ferromagnetic materials, the relationship of magnetization to external magnetic field is different when the external field is increases from when it is decreasing. So here such type of relationship is explained. When the materials is magnetized to saturation, and then the external field is reduced to zero, some magnetization again remains. This behavior is characteristic of permanent magnets, which retain most of their saturation magnetization when the magnetization field is removed. So to reduce the magnetization to zero requires a magnetic field in the reverse direction, and this behavior is hysteresis, and the curves are called hysteresis loops. And magnetizing and demagnetizing a material that has hysteresis involve the dissipation of energy, and the temperature of the material increases during such a process. And it's why it's important, because ferromagnetic materials are widely used in electromagnets, transformer cores, motors and generators, in which it is desirable to have as large a magnetic field as possible for a given current. Because hysteresis dissipates energy, materials that are used in this application should usually have as narrow hysteresis loop as possible. So soft iron is often used. It has high permeability without appreciable hysteresis. So for permanent magnets, a broad hysteresis loop is usually desirable, with large zero field magnetization and large reverse field needed to demagnetize. Many kinds of steel and magnetite are commonly used for permanent magnets. The remaining magnetic field in such a material after it has been magnetized to near saturation is typically of the order of 1 Tesla. And here this hysteresis loop is hard to demagnetize, and it is good for permanent magnets. Here it magnetizes and demagnetizes more easily. It could be used as a computer memory material, such type of material which has such type of loop. And this type of material is useful for transformer and other alternating current devices where zero hysteresis would be optimal. So it's a behavior of different materials, ferromagnetic materials. And if I would appreciate if you do a reading from about magnetic materials from your advised books, like from Halliday or from University Physics, and then if you will find any problem or any confusion, you can discuss with me, because